Hello everyone, today we're gonna do the shear and moment diagram for moving loads. These moving loads is the moving loads number 2. The first one we did was I placed the well, last well, 1 foot away from the center line of the support. Today I moved the loads and I place it like 5 feet away from the center line of the support. That's why I put it over here. Now this is 5 feet away. See what happens. We're gonna solve the shear and the moment in that particular position here. As you know, the load is from the AASHTO. The load per the stroke is, the name of the load is HS20-44, and this type of loading maximum well is 32,000 in the rear, the middle as well is 32,000, the front well is carrying 8,000 pounds. These are the maximum loads for this type of loading. Okay. The well there is the combined wells, and put it in one. Alright, so at 5 foot away from the support, see what happened. Total loads, the total of this load is 72,000 pounds. Span of bridge 60. The distance between front and the middle wheel, this is typical 14 feet, and distance between these two wheels are variable from minimum 14 up to here to the maximum of 30 feet. Here I choose 20, and here are the tools. Here's the tools when you solve the shear diagram. The shear is moving towards the load, and the meeting line there is the point where you calculate the shear and the loads. Okay, you're gonna do a counting here, like this point here. The 21 will travel and stop at that line there because there's load coming down. Let's calculate. Calculation occurs here. 21 then minus 8,000. That's why we have 13,000 here, right? This point here now is 13,000. Okay, because it's there's a negative load coming down, so therefore the 21,200 is reduced to 13,000. Okay, so this is very helpful for the shear diagram. This is the actual path. This is the load path for shear diagram. Concentrated loads only. Okay, and this is sign convention here. Clockwise is positive and counterclockwise negative. Going down is negative, and upward force is positive. Okay, let's go solve for reactions. Solving for reactions, I recommended moments only. Okay, for both reactions. Summation of moment R2 equals to 0. First equation, then summation of moment R1 is equals to 0. Is the most accurate way in solving reactions. Okay, let's go solve for the reactions. To solve reaction 1, you have to take the moment the reaction 2. So summation of moment R2 is equal to 0. The R1 now is going clockwise, and the lever arm for R1 is from here up to here 60. Okay, this is 60. And okay, R160 now, and the first load from R1 from R2 is this one here, 32,000 pounds times 5, and the second load is 32,000 again. The lever arm is 25, and then the next load is 8,000. From here, that's the lever arm, multiply that, so 20, 14 plus 5 equals 39. Okay, so that's why 8 times 39 we have there. So 60 R1 now is equal to, we calculate this one is 160, this multiply this is 800, and then 8 by 39 is 312. R1 now is equal to 1272. Altogether you add that, divide by 60. The lever arm for R1 is 60. R1 is 21,200 pounds, and I plug it over here. Alright, that's R1. Now R2. To solve for reaction 2, we have to take the moment at R1. Okay, when you take the moment, the as axis of rotation, any forces going there, passing through there is equal to 0. So therefore R1 becomes 0. You only have R2 as the unknown. Okay, now R2 is going counterclockwise, whereas all these loads is going clockwise, so therefore they are equal. You have to equate that. It's a shortcut method of transposing member of the equation to the other side of the equation. So 60 R2 now is equal to 8. The first load from summation of moment R1 right here, take the moment there, you look at the load, the first load is 8,000 coming down. 8,000 times, the lever arm is 21, so right here 8 times 21, and the next load is 32,000, and the lever arm is 21 plus 14, that's 35, so 32 times 35 is right here, and the third load is 32,000 coming down, and the lever arm to R1 is 20 plus 14 plus 21, that is 55, so 32 times 55. So all the loads are in, so now 60 R2 equals to, you work this out, multiply that, add that, multiply, it comes up 168 for this, 1120 for this, and 32 times 55 is 1760. You add all this up, and then you divide it by 60, you get R2, 50,800 pounds. So R2's right here. Now to make sure the reactions are correct, you gotta check the reactions by using summation of vertical forces is equal to 0. This is the only time that you're gonna use the summation of vertical forces is equal to 0 to check your reactions. So what is summation of vertical forces equal to 0? So the going upward R1 plus R2 is equal to the load coming down, all of these loads. R1, R2 going up, and all of this coming down. So equate that. So R1 now is 21,000 plus 50,000 must be equal to 72,000 pounds. So you add this up, it becomes 72,000 is equal to 72,000. Therefore reactions are correct. You never have to go continue when you have an error here. Okay, you have to go back. But since this is equal, and use the moment only, okay, to solve for reactions. Never mix this up with the vertical forces. Okay, moments only. Alright, so now we have reaction Reaction is correct. Now let's go to solve for the shear. Okay, the shear shear diagram. Start with the reaction. 21,200. You gotta calibrate this line and locate the point of 21,200. So that's I located 21,200 line, and now that is the shear at A. Okay, starts with that reaction there. Now shear B, right here. Shear B is 21,000. Follow this load path there. The shear going there and meet with the load coming down. This intersection here you have to calculate. All right. So that's why I draw this path, so that will help for the shear diagram. You didn't get lost. And then with the sign conventions, alright, right here, downward negative, upward is positive. So since 21,000 is above the shear line, this is the division between positive above and negative below. Alright, so this is the path for the shear diagram. Okay, now 21,200 will travel horizontally. You draw that line and meet this load coming down 8,000 pounds at that point there, and then you calculate. So 21,000 positive minus 8,000 right here, it's called 13,000. That's why we have 13,000 right here. That's for the shear for B. Shear B. Now shear at C. Okay, the shear at C, the 13,200 will travel. Since there's no load here, it's a horizontal line. From that point there, you draw up to that line there, meeting again, following the path. Okay, to meet that load there coming down, which is 32,000, and what is that? It's coming down negative, right? So this is still positive. So shear at C now is the 13,000 minus that load coming down there. Minus 13,000 becomes minus. Since 32 is greater than 13, you retain the sign of the negative sign. So 18,000 right here. The 13,000, when we reach this line, the 32,000 pushes it down below the shear line, so it becomes negative 18,800. So from this point here, you draw a line. You look at above, there's nothing there, there's no uniform, there's no load. So when there's no load, from this point here, you draw a line up to meeting again, and look at the load that's coming down, and you stop there. Again, the path, you look at this all the time, and that intersection there, calculation occur. Alright, so shear D now is the 18,000. Draw horizontal line. 18,000 will travel here and meeting with 32,000 pounds coming down, and since they are both negative, the coming down 32,000 is negative as well. They join together, you add that up, retaining the sign becomes 50,000 at D. Right here, minus 50,800. Okay. Minus 50,800 will travel again, draw horizontal line to E. To meet, and finally the reaction, which is 50,000. Okay, so 50,000 minus, and then the reaction pushes it up, positive going up, and you add it up, minus and negative and positive. The shear B, the shear E, okay. The shear is represented as V, okay. Shear A is 50,800 negative 50,800 plus 50,800 is equal to 0. Alright. Shear A is 0, and then therefore the shear is closed. Once you end up 0, meaning all these calculations, they're correct. Once you know they are correct, because we end up 0, if it doesn't end up in 0, then something wrong there. You gotta go back. You cannot proceed to solve for moments unless you get the 0 here. Alright? Okay, now solve for moments. Solving for moments, we need the areas of this figure, all these figures. This is AB, it's a rectangle, and then BC. I use different colors so you can see properly. BC, CD, and DE. So the area of AB is the 21,000, the height, and the span is 21. Alright, so the area of AB is 21,000 times 21 is 445,200 foot-pounds. That's area AB. Now BC. The BC is right here. The height of this is 13,000. You already done that. Okay, you screwed that. Now you're here. You're in this side. 13,200 multiplied by the lever arm of 14. So BC now. BC is 13,200 times 14, 184,800 foot-pounds. Okay, that's BC, the area that. Now the area CD, this is CD. Okay, area CD is, you look at the shear there is 18,800 as a negative. The height of this is 18,800. To get the area is you multiply it by the width, which is the lever arm of 20. Alright, the area of that is 18,800 times 20. That's why the CD is minus 18,800 times 20 is equal to negative 376,000 foot-pounds right there. This area here is 376,000 foot-pounds. Now we're done with that. Now let's go to area DE. The height of the area DE, this figure here, is 50,800. The height of that multiplied by the lever arm, this is 5. Alright, so DE now is minus 50,800 times 5 equals to minus 254,000 foot-pounds. Okay, we're done with the areas. As we know, we need areas to solve for the moments. Now solving for moments. Moment at A is 0, start at 0 in the beginning of the moments. And moment at B. Okay, moment at B is the area here, right? That is the moment at B. The moment at B is the area of AB, which is 445,200. So that's 445,200 right there. You plot it right here. Alright. And now moment at C. all these moments is carried over. The moment here is not just this one here, it's added. You add the moment all the way up to the end of 0. So what is in here is this 445,200. Now add this area here, the BC. So moment at C, now moment at C, see, 445,200 plus. Where's 184,000? The 184,000 right here is a BC. Right there. So meaning, if you look at the graph, this area here added to the area here is the moment over here. Okay. So the summation of these moments, these two moments, is the C. You gotta look at the line properly. This side here, all this moment is the moment there. So yeah, moment at C, 445,200, the area there, plus 184,000, the BC, it's equal to 630,000 foot-pounds. That one here. I put here, that's the C, 630,000 foot-pounds. Now, moment at D. You're only here. The moment of D, there's area here, CD. So the 630,000 pounds here, foot-pounds, plus this area here. What is that area? CD. The CD is 376,000, and it is negative. So 630,000 minus 376,000 is equal to 254,000 foot-pounds. You look at the sign here. The 630 is greater than 376. Therefore, the sign is still positive. Okay, still above the shear line, the moment line here. Okay, again, this is the separation of positive and negative. Even it's in the negative sign here, but the positive is greater than the negative right here. So therefore, it's still positive, 254,000 foot-pounds. So where is 254,000? If that is 630,000, the 254,000 is around here. See, I draw a separate moment so you can see. This is the 254,000 foot-pounds moment. This white here, this white moment is 454,200, and this magenta color there, this is the 630,000 foot-pounds. This is by far, I think, the maximum moment. So now we have positive 254,000. The moment at E here is this moment here. You stop there, and there's a moment here, right there. That area there will be calculated the same as this one. Okay, same as this path here will be calculated right here. So 250,000 moment at E. Moment at E now is 250,000 right there. Now there's a moment minus, and this area here, DE, you gotta look for the DE. DE is minus 254,000 foot-pounds. So you sum all this up in up 0. So therefore, moment at E is equal to 0. Alright, so we got the shear 0, we close that, and we close the moment as well. Therefore, all of this values we have are correct. And now you look at all the moments. The maximum moment is the largest moment of all these moments here. The largest moment is at C, and it is 630,000 foot-pounds. Alright, and then you draw the conclusion when distance x is 5, okay, when the wheel is 5 feet away from the center line of the support, maximum moment is 630,000 foot-pounds at joint C. And when the distance x is 5, this is the x distance, distance of the moving loads. The maximum shear is equal to 50,800 foot-pounds, and it is at joint D right here. That's where the maximum moment, maximum shear force right there. As I mentioned before, the idea of the location of the most critical shear of any horizontal member subjected to loads is that shear location is a very close distance from the face of the support. Okay, you can't get any larger than that there. That's the location approximate. That's why on the first video right here I started a very small pace there to see the most critical shear. This is the largest shear. When the wheel is 1 foot away, look at the shear here. The shear is 55,600, and for the second video is 5 now. It becomes smaller and smaller up to the midspan become like 0. The diagram for shear is going like this, going down to the midspan. This is the largest shear, and it goes inclined like that, and it goes negative all the way to the other reaction. See, this is the testing rate. See, 1 foot. This, you can't get any greater than this shear for sure. I know that. 55,600. Now, for the second moving loads, it's moving 5 feet away. Look at the shear. The shear is only 50,800. When I move this to 10, it's gonna get smaller and smaller. Alright, so that's the end of the video. I think we did pretty good in this shear moment diagram. These are all correct because we verified that. Alright, that's the end of the video, and see you in the next video. I'm gonna continue until I get the smallest maximum moment. Right here at 5, you get 630,000 maximum moment. How about 1? Okay, smaller moment. When the distance of the wheel is 1 foot away, the maximum moment is only 527,000. As the maximum moment, I know this when moving loads, the center of the span, you're gonna get, that's the highest maximum moment there. So we have to compare the moments while this load is moving along the span of the bridge. That's why we solve it one by one, step by step. So at 5 feet away, 630,000 now. Now it's getting bigger and bigger. And the next distance would be, I think, I'll put, this is 60 feet of span of the bridge. I will go for 10 from the support. Alright, see you next time, and this is the end of the video. Thanks for watching, and bye bye.